So can you just check the message?
I think we can start straight away.
Will I stop sharing for a second?
No, Praveen?
Yes. Can you just read the message? Just. So I just wait for 1 minute, Kailas up to join.
Okay, we're just going to wait for a second. That's fine.
Just a second. Okay, fine. I mean, it's okay. So we can actually start. So welcome everybody to the 8th lecture of our webinar series. Now I invite our director, Professor Pramod Gopinath, to formally chair the session and to introduce the speaker to us. Thank you very much. Pramod sir, please.
Thank you, Dr. Praveen. It's been a pleasure to meet Professor John Costello, because we have been in contact, I think, since 2005. I was working on a postdoctoral fellowship program. We were planning for a joint UKRI postdoctoral scheme we were working out when I got my first job at Indian Institute of Space Science and Technology. So we did not proceed with that project further. So let me formally introduce Professor John Costello. John Costello is full professor of physics in the School of Physical Sciences at Dublin City University and a founding member of the National Center for Plasma Science and Technology. He served as the head of the School of Physics from 2004 to 2009, Associate Dean Research from 2009 to 2011, and Dean of the Faculty of Science and Health from 2011 to 2016. He is a fellow of the Institute of Physics and a chartered physicist. He is a recipient of the 2017 DCU President's Research Award. His research interests lie mainly in intense laser matter interaction with a special interest in laser plasma generation and photoionization processes, most recently in VUV and X-ray Photoelectron laser fields. He was one of the very first people internationally to gain competitive access to the world leading facility, the Flash FEL at DESY Hamburg, when it first opened to users in 2005, and also to the LS X-ray FEL at Stanford, when it opened in 2009. He and his collaborators have since made many of the seminal contributions to atomic physics with FELs. These include 4 FEL papers in the foremost physics journal, Physical Review Letters, and 7 in Nature titles. He was the lead editor for a special issue of the Journal of Modern Optics on FELs in 2016. He has been a visiting scientist at various international institutes, including NIST USA, DESY Berlin, DESY Hamburg, RAL UK, LCLS Stanford, MPIK Heidelberg. John has published over 150 refereed journal papers, which has been cited more than 4,400 times on Web of Science and 6,300 times on Google Scholar. He has also made over 250 conference and workshop presentations on these topics, including more than 50 invited talks at international conferences and workshops. He is a member of the editorial board of Applied Sciences and the Journal of Modern Optics. He reviews proposals for many international funding agencies and has chaired and served on a number of EPSRC funding prioritization panels. He is a vice chair of peer review panel for the new European X-ray FEL small quantum system facility in Hamburg. With this brief introduction, let me welcome Professor John Costello for our webinar series, and I invite him to give the talk. Over to you, Professor John.
Thank you very much, Pramod, for that very kind introduction. It's a real honor to be invited to speak in this series to celebrate 25 years of the International School of Photonics. It has a global reputation now, and it's clear in the quality of the outputs and the quality of the students that you produce and so on, that this is really a world-class institute and a world-class school for photonics. And it's very welcome in the area of photonics. So congratulations on 25 years. And we wish you many, many more years in the future. I'm just going to share my screen. When I sent the title, I didn't think it was so ambitious as AMO Physics with VUV and X-ray FELs, because if I was to use that broad very generic title. We could be here for weeks. So I'm going to focus. Let me just move to full screen. I'm going to focus it a little bit, and I'm going to focus it on atoms. I'll say I have one slide at the end on molecules, but I'm going to talk about atoms because I'm with Arthur Shallow when he was asked to define a diatomic molecule, and he said it's basically one atom too many. So molecules, I've managed to make a career by avoiding molecules up to very recently, almost a 40-year career in AMO Physics, avoiding the M. And so I want to talk a little bit about atoms because I think we're coming to the end of atoms. Just to say who we are in DCU, we're sort of a mix of a laser plasma group and an AMO group. We have 6 different laboratory areas, and they're focused essentially on laser matter interactions. So we do some spectroscopy from the UV to the extreme UV. We do a little bit of infrared and visible as well. We do some imaging. We can do that in any spectral range from the X-ray to the near infrared. And we have a little bit of particle detection going on. And so these are some of the lab areas. This is a pulse laser deposition system. We do some materials deposition with lasers. That's an example of one of our 1 meter normal incidence VUV spectrometers. That's our ultra fast femtosecond lab. That's a picture from a plasma diagnostics lab where we do some colliding plasmas experiments. This is a very old picture, but I like it because it shows one of the kind of early experiments and experimental setups we had. And the way to look at that is there's basically 2 laser plasmas here. One of them is an extreme ultraviolet source like a synchrotron, and the other plasma is a sample, and we can do time-resolved photoabsorption, and this is a grazing incidence spectrometer. I didn't have a nice picture of it, so I took this is from a very old thesis back in the early 90s, but it illustrates that we can do ultra fast spectroscopy, we can do pulse laser deposition, we don't do all these things at the same time, but we have the capacity to switch them on at any one time. Just to say again, we are 5 people, 1 theorist, Lampros Nikolopoulos. Me, I mainly work with free electron lasers and laser plasmas, and Eugene, Jean-Paul, and Paul mainly work at synchrotrons and also a little bit on laser plasmas. Jean-Paul is the guy who does the pulse laser deposition stuff. So currently, these are the students we have: Mohammed, Sadaf, James, Adam, Andrew, and so on. There's one postdoc working with us, a Greek guy, Lampros Nikolopoulos, really very, very good, very clever guy. And these are some recent PhD graduates, Nikki, Stephen, Get, William, Lazarus, and so on. So we have we're quite busy. So let me just outline the talk. I'm going to talk very briefly in 1 or 2 slides about short wavelength free electron lasers, so-called SASE, or self-amplified spontaneous emission-based lasers. So they're really amplified spontaneous emitters. They're not really true lasers. Now, when I say that, some of the more modern free electron lasers, like for example, the Fermi free electron laser in Trieste, is injection seeded. So it's a truly fully phase coherent FEL, and there's lovely things you can do with it. I'm going to mention 2 things. I'm going to mention, looking in the VUV, one recent experiment on 2 photon double ionization of krypton. So normally we think of 2 photon and 1 electron being ionized, or we think about 2 photon absorption. This is 2 photons, 2 electrons. I'm going to then talk a little bit of what's known as the atomic street camera, a concept which was developed between people like the Corkum group in Canada, in Ottawa, and people at MPIQ in Munich. And now it's worldwide. There are probably 20 groups with atomic street cameras. And I'm going to talk how we adapted one of those in order to measure a time delay. So there's a big interest in time delay in photoionization, and there are groups all over the world, including in India, who are interested in measuring time delays in photoionization. So I'm going to talk about a recent experiment where we measure the time delay between a photoelectron being emitted from an atom, and then as the atom relaxed and an Auger electron, a secondary electron, was produced, how do we measure the time delay between the photo and Auger electron? I'll mention something about next steps and then I'll finish off. Just to show you, this is a picture from the control room at the LINIC coherent light source at Stanford. And the reason I put it in is that there are some important players in this picture. Michael Meyer from the European X-FEL, Wolfie Helmel, who comes from the, he was in Munich, Wolfe is now based in Dortmund. Adrian Cavalieri, who has recently moved to SwissFEL, the new Swiss free electron laser. Reini Kienberger from the TU in Munich. John Bozek from Soleil in France. Ryan Coffey. So these people, I mean, when I look at the pioneers of AMO physics with FELs, John Bozek, Reini Kienberger, Michael Meyer, and then you can see some of the younger ones like Adrian Wolfe and so on. So this, fortunately, and Andreas Meyer here, Stefan Duster, unfortunately, we're not terribly well gender balanced. This was work actually on, we were doing an experiment which was related to Ivanka Gurgas here, to her PhD. So just to orient ourselves in terms of FELs and so on, if you think about a free electron laser, think about an ultra fast laser working in the X-ray. So think about a femtosecond laser working in the X-ray. So just to orient ourselves, we're used to lasers operating in a photon energy range from a fraction of an electron volt to a few electron volts. And so most of the research with lasers, and still today, most of the research with lasers is in this relatively narrow band here. We're on a log scale. Very little in the vacuum ultraviolet. And the opening up free electron lasers in the early days got us into the VUV and the extreme UV. And then when LCLS came along in 2009, we started to get into the soft X-ray and all the way up to what David Atwood calls hard X-rays. Some of the medical physics people might disagree with you there. But certainly it's possible to produce at least spatially coherent femtosecond duration pulses with energies up to a millijoule or a couple of millijoules at a wavelength of 1 angstrom. And if you were to say that, I mean, if I said that 30 years ago, people said that's not going to happen because we had plasma-based lasers, which were not very efficient. The pulse durations were on the order of tens of picoseconds. The energies were fractions of a microjoule. There was no way we could produce the kind of irradiances, intensities that you can produce with these lasers. So if you think now in terms of a millijoule in 10 femtoseconds at a wavelength of 1 angstrom, focused to a few nanometers, you're talking about focused intensities of 10 to the 20, 10 to the 21 watts per centimeter squared. So not only can these lasers produce ultra short pulses, they can produce ultra high intensities. Just to orient ourselves a little bit, when you think in terms of timescales, we're down in this timescale region here. And so when you're down in the femtosecond timescale region, if you look at doing rotational spectroscopy of a simple diatomic molecule, you think in terms of picoseconds for larger molecules to tens of picoseconds. If you do vibrational spectroscopy, particularly for small diatomics and so on, you talk about a few, few femtoseconds in terms of vibrational time constants. If you think about electrons in atoms, and if you take a sort of a Bohr atom approach to life, and you think about what's the typical period for, say, a 1s electron in hydrogen, you can do a rough calculation. It'll come out around 150 or so attoseconds. So if you're doing electron spectroscopy in atoms, then you're talking about 100 attoseconds. Here, you're talking about a few femtoseconds, and here you're talking about a few picoseconds. So they're the sort of timescales. And X-ray free electron lasers get us into this business, and more recently get us into this timescale here. And there are various tricks you can do that. So the holy grail basically was to get a VUV to X-ray laser with variable pulse duration, which was on the femtosecond to attosecond timescale, tunable wavelength, so you can tune it all the way from the ultraviolet to the X-ray. So you can tune it from something on the order of, say, 1,000 angstroms to 1 angstrom. You could vary the polarization, and there are ways to do that with modern free electron lasers, and a relatively high energy per pulse from a few tens or hundreds of microjoules, even up to a few 10 millijoule. And so in certain modes at certain wavelengths, for example, SACLA, which is one of the free electron lasers in Japan, you can push it towards 10 millijoules. XFEL at Hamburg, you could certainly push it towards 10 millijoules without any monochromatization or so on. This is a very old picture, and I use it a lot because it illustrates the basic elements of a free electron laser, an X-ray free electron laser. So you start off essentially with an ultra short UV pulse here on the order of maybe 100 femtoseconds. You have a photocathode, you produce an electron bunch. So you have a pulse laser which produces an electron bunch. That electron bunch is then accelerated down a linear accelerator, down a LINAC, depending if you're in the EUV or XUV. So if you're at a photon energy of say 100 eV, then you're probably going to have something, a LINAC, which is maybe 200, 300 meters long. So that's the case, for example, at Fermi in Italy and Deci in Hamburg with flash. If you want to produce X-rays, say at 1 angstrom, then you're probably going to need something like a 15 to 20 giga electron volt GeV LINAC. And so this thing will be a couple of kilometers long. So that's the European X-FEL, SACLA in Japan, Swiss FEL, and also the linear coherent light source at Stanford. You take your electron bunches and you inject them into an undulator. And an undulator has alternating north-south poles. So when the electrons enter the undulator, they undergo a slalom type motion. And if you get everything right in terms of the energy here and phase matching and so on, what you'll get coming out of here is the electron bunch, different to the electron bunch that went in. It'll be spatially structured, and also X-rays. And those X-rays will be coherent. They're spatially coherent. They won't be temporally coherent. They'll be spatially coherent. You can show that by just doing a double slits experiment with your X-rays, and you'll see the fringes. So it's spatially coherent. And then you usually use a magnet here to dump the electrons. So you deflect the electrons, and then you collect the X-rays and use them for whatever you want. So what you've got coming out of here is a train of X-ray pulses, typically, you know, a millijoule, 100 femtoseconds, at a repetition rate, which depends on the repetition rate of this guy here. At LCLS, it's a pulsed RF system for the linear accelerator, so it's up to 120 pulses per second, whereas tens of kilohertz, you know, pulse repetition frequencies of tens of kilohertz at things like X-FEL are possible. So because it's a superconducting, in fact, in principle, up to a megahertz. So this is an old picture as well, but I like it because it kind of illustrates the principle reasonably well. You inject an electron bunch in here into the undulator. So the LINAC is up here. You inject your electron bunches. They undergo a slalom type motion. And what comes out the end here is an X-ray. And in a way, what you're trying to do is you're trying to get a fixed phase relationship between the electrons as they traverse through the undulator and the X-rays. And what's happening is you're using the electrons to feed the energy of the X-rays, but you want those X-rays to coherently add as they go along. And so if you want to do a relationship between the spatial period of the undulator, what's the spatial period? So you might have north, south, north, south. So from here to here might have a spatial period of 3 centimeters. So this guy here might be something like 30 meters long. The spatial period lambda u here might be about 3 centimeters. The electron bunch is passing through at close to the speed of light. So for a 1 GeV machine, you might have a gamma of about 2000. And if you substitute in basically into this expression here, that effectively the X-ray or EUV laser wavelength or XUV laser wavelength is essentially the spatial period, which is in centimeters, divided by 2 gamma squared, which will now be in a few million. And so you go down from a wavelength of centimeters down to a wavelength of nanometers. Excuse me. And typically that laser, these are typically the characteristics which you'll have for flash. It's typically a gamma. It's a little bit higher now. It's probably closer to 2.5, 2800. And you can get a wavelength down to about 3.5 or 4 nanometers. The gamma is significantly higher when you go to X-ray FELs because you need to get this wavelength down from typically a couple of centimeters down to 0.1 of a nanometer or so on. So essentially, you inject your electron bunches in, they undergo this slalom type motion, and what you get out the other side are your X-rays. There's a little bit of geometry you can do, which gives you a little trick, which does that there, which is not quite completely physically accurate, but it gives you a good order of magnitude on the relationship between the energy and the electron beam. So what's the energy in the electron beam as you inject it? Is it GeV? Is it 100 GeV? What is it? And the wavelength. That comes in the gamma. The magnetic field actually comes in because if you do the kind of analysis that people like Mikhail Yurkov, for example, and Evgeny Schneidmiller have done, and many other people. It turns out that this is a more accurate expression. This is the actual expression relating the undulator period to the X-ray wavelength. And in that case, you can see it depends on the magnetic field as well. And so there are two ways that you can tune lambda L. You can either tune gamma by tuning the electron bunch energy, or you can tune it by changing B. And so there are two types of undulators. There's the fixed gap undulator, where you change the electron beam energy and that changes the X-ray wavelength. I can tell you from experience, working with machine people, that's painful at times. But if you've got really, really good engineering and high precision engineering, then what you can do is you can change the gap. And if you change the gap, you can change the B field, you can change K, and you can change the wavelength. So you can have a variable gap undulator for tuning the X-ray wavelength, or you change the electron beam energy. This is typically what, excuse me, this is just an illustration from Brian McNeil at Strathclyde University in a paper that he published on X-ray free electron lasers back in 2010. And essentially what you see here is you get, here's your electron bunch, which is injected, and it undergoes this slalom type motion as it propagates along the undulator. What happens is, as it starts to emit X-rays, that X-ray field interacts with the electrons. And as the X-ray field itself becomes more coherent, the electron bunch becomes more spatially coherent. So you introduce a spatial period on the electron bunch itself. And so you get a sort of feedback mechanism going on here, where the more spatially coherent the bunch, the more coherent is the X-ray field. In other words, the more phase locked become the various components. This is a rather, it's a simplification, but you get the idea that as this bunch moves along here, it becomes more and more spatially coherent, which means the X-ray beam becomes actually more and more spatially coherent. So you end up with, and so you get the spatial structure. So the spatial coherence in the bunch is acting regeneratively with the X-ray field, and the two of them act together. And so what you get out the end here tends to be an X-ray pulse, which is a little bit, it's pretty spatially coherent. But most of the papers, if you pick them up on characterization of X-ray FELs, will show you a young slits pattern. And you'll see that the modulation, the contrast transfer function across it is pretty good. So they tend to be very spatially coherent. And that's one of the reasons why people like them, because you can do things like coherent diffractive imaging of mimiviruses, biomolecules, nanoparticles and so on, because they are spatially coherent, and you can do it in a single shot. So you can do single shot imaging, for example, of protein crystals as well. And protein crystals, as you may know, is a big business at synchrotrons. About half the proteins have not been structured because they can't make big enough crystals to get a big enough signal at synchrotrons. But even very small crystals, because of the intensity of the FELs, will give you very nice CDI patterns. So it's a huge area of research with people like Henry Chapman and many others in that area, Petra Froma and many others. This is an old picture. I want to show you the layout of Flash in the early days, and this is the original hall. This was the Expo 2000 hall in Hamburg, which became essentially the end of the beam line. This is the beam line coming in here. This is the Flash hall. And so this is what the structure looks like. When you create these electron bunches, of course, they want to cool and explode. So what you want to do is you have to keep recompressing them and so on, so that you can keep the electron bunch reasonably short, because when you inject it into the undulator, you want it to have a duration of less than a picosecond. And because it essentially has a current distribution in time, what you tend to see with these free electron lasers is you only get lasing at the peak of the bunch. So even if the bunch is a picosecond long, the pulse duration tends to remain only at about 100 femtoseconds or so. So, excuse me, the free electron lasers are under constant development. And so although you may keep the same LINAC, what's happening globally is that for the more established free electron laser facilities, they have to keep up with the new ones. And so here at Flash, for example, they've put in a second set of undulators. These are variable gap. So here's the fixed gap where you have to change the beam energy, the electron bunch energy. Here's one where you can keep the electron bunch energy fixed and just vary the gap. So they now call these buildings the Albert Einstein and the Chi Sigman buildings. And you can see the scale of the laser. It's about 315, 320 meters in total from photocathode to end station. So that's what's happened at Hamburg. If you go back to 2011 and looked at an overview, so this is a picture taken of the SLAC, Stanford Linear Accelerator site, that part of it where LCLS, the Linear Coherent Light Source FEL is. And you can see there are two experimental halls known as the near and the far. We used to work in the near experimental hall at the AMO station. And essentially they were using initially about 600 meters of the accelerator. There's more of it being used now because they can go to higher energy. So this is the old LINAC going back to the late 50s and early 60s. So, you know, they've had the LINAC for a long time. It's pulsed. You can get it at 60 or 120 pulses per second. And you can, they're you know, pump probe experiments, X-ray diffraction and imaging, materials under extreme conditions and so on. Well, of course, they couldn't sit still and they're building a second one called LCLS2, which will now have a superconducting accelerator. What that means is instead of having 100 pulses per second, they will be able to produce 1 million pulses per second, they think. Good luck with that. I've heard that before at lots of what's called CDR, conceptual design report stage, usually due to heating and all kinds of other issues. They rarely do we see these things go much above about 100 kilohertz, a PRF of 100 kilohertz. But even that's great because you can think about huge flux in each pulse and be able to do coincidence experiments where you might have you might have multi-electron ionization along with multiple fragments of a molecule, and you want to detect all these things in coincidence. So here are the various end stations: atomic molecular optical science, AMO, that's us, soft X-ray, X-ray pump probe, correlation. Now, what you tend to find with all of these things is they all, you know, the fact is you can do X-ray pump probe there, and you can do it here as well. This guy here is mostly about crystal spectrometers and so on, and doing things like X-ray fluorescence. Okay, that's some background on free electron lasers, and they're being built everywhere. So you have Pohang in Korea, Shanghai, Dalian has a VUV one in China, Shanghai, Swiss FEL. Look, there will be many more in the years to come, and lots of opportunities to work at them. They are accelerator type experiments, so you tend to end up with lots of authors and papers. So I'm going to take this one because it's a fairly recent experiment we did. It was part of the PhD of this guy, and we have lots of collaborators because we're part of a big collaboration. And this is a very, very simple experiment, okay? And I'll just illustrate it here. Effectively, you've got a krypton atom, and you have a single free electron laser pulse, not two pulses, just one pulse. And it's so intense that in the early part of the pulse, you ionize a p electron, you ionize a valence electron. And within the same pulse, which might only be 50 or 60 femtoseconds long, you ionize a second electron. So normally, when you think about two photon ionization with an optical laser, you do think about valence electrons, but what you think about is I absorb my two photons simultaneously, what's referred to very often as direct two photon, but it's usually single electron ionization. So you have two photons absorbed, one electron goes out. This is a sequential process. It's two photons. You end up the product being a doubly ionized atom, but it's two photons belonging to the same pulse, one after the other. So it's two photon sequential. Now, to illustrate the process, to illustrate the process, what happens is your first photon comes in and it ionizes krypton in its ground state, 4p6 singlet S. And you're then left with a krypton plus ion, and a krypton plus ion in the ground state has two spin orbit split components, obviously, right? Double a p3 half and double a p a half. So now with the same photon, you can ionize the krypton plus. And where's that going to leave you? Well, it's going to leave you with krypton 2 plus in this state here. So the electron configuration is 4p4, but the only terms of 4p4 which are accessible at this photon energy are the triplet p's. And the singlet D2 and the singlet S are not accessible because the photon energy is too low. And that's specifically, we specifically wanted to look at what happened when you looked at the emission of these electrons from krypton plus, where they were very, very close to the ionization threshold. One complication here, which we didn't think about when we were initially doing the experiment, so hands up on that, is that actually there are resonances here. Now, I should have thought of that because I published a paper many years ago on these, but anyway, that's another story. So you have essentially an excitation here, a 4s to 5p excitation. And there are actually some doubly excited states sitting in there, which we don't show as well. So there's some doubly excited states, which are 4p6 to 4p4 NL, N prime, L prime states as well. And the same thing happens up here. So what complicated the analysis a little bit was the fact that there were quite a deal of resonance structure. And something to bear in mind is that the bandwidth of a free electron laser is quite large. So this is a 25 eV roughly photon energy, and we had a bandwidth of half an EV. So we overlapped quite a few of these states. So when we created this state here, that state there undergoes an Auger decay to here, but you can still have a direct pathway where you ionize and you're left with these states here. And what happens is you just get essentially a normal Auger from here and you end up there. So anyway, these are the pathways. So you can go through a resonance or you can go directly to krypton plus plus an electron. And then from the krypton plus with the same photon energy, you can go from krypton plus to krypton 2 plus, leaving you in these states here with an electron. So we have two electrons. So we have two photons, 1 and 2, and two electrons. And so we were interested in studying from a fundamental perspective with our Russian colleagues, we were interested in studying the angular distribution of these electrons and how they might be different to synchrotrons. So this is roughly what the experiment looked like. It's very, very simple. We have a spectrometer down here. It's a so-called velocity map imaging spectrometer. So there are kind of two ways. Imagine you have an atom and a photon goes in. The pattern, the shape or pattern of the electron emission depends on the orbital from which the electron is emitted, whether it's an S, a P, a G, whatever it is, right? And we were dealing with P orbitals, so we expect some kind of a small asymmetry. So essentially what we do is we focus our X-ray beam in here, and then we want to measure the angular distribution. So what you can do lots of things. You can either have an electron detector that you rotate around here and rotate around there. It's complicated because you have to take lots of shots. Some colleagues have made a thing called a cookie box where they've made 16 time-of-flight electron spectrometers, which essentially are in a circle around the interaction region. The other thing to do is to take the electron pattern and image it onto a two-dimensional detector. And that's what a VMI does. It takes the pattern of the electrons, and then with a series of electrodes, which are really electrostatic lenses, it images the electron pattern onto a microchannel plate detector, and then that's imaged with a CCD. And the problem is that you're taking a three-dimensional pattern and squashing it down to 2D. And so people cleverer than me have tricks like A-bell inversion and so on to take this 2D pattern and take slices of it, for example, and then be able to reconstruct it. And in reconstructing it, you end up with a pattern which looks like this. So what you have here is you see some rings. And so the way to look at this is the electron kinetic energy. So this is the atomic photoelectric effect, you know, the photon in, electron out, and the energy is the photon energy minus the ionization potential. Simple as that. So out here, you have high kinetic energy, and there's actually two rings here, and they correspond to the two electrons which leave the neutral krypton and then leave behind it krypton plus in two possible final states, WP1/2, WP3/2. And so out here, this essentially corresponds to the kinetic energy. And of course, you can see that you generate circles because, you know, the kinetic energy doesn't vary with angle. Now, what does vary is the intensity, and that depends on the spherical harmonics. In here, these features in here, this guy, and this guy, they're from krypton plus. So that's krypton plus becoming krypton 2 plus. So you can see that the energies, this is zero energy in here, the energies are getting much closer to zero. So what you can do then is you can unfold this guy here and unfold these guys. And this then gives you what the angular distribution looks like. So we have angle along here in degrees. And here we essentially have the radial position. So we have kinetic energy. So here, kinetic energy close to zero. We calibrate these things obviously afterwards with known photo lines and so on. So here you can measure the angular distribution of the emitted electrons. So the first thing you do is if you integrate along here, forget the angular distribution, you can essentially get the kinetic energy spectrum. You can get what's called the photoelectron spectrum or the Auger electron spectrum. In this case, they're photoelectrons. So we're dealing with photoelectrons only. And so these three up here corresponds to these three guys here. And then at higher, up here at higher photon energy, that's two guys down here. You can see that they're just about resolved. So the first thing we have to do is we have to try and calculate, excuse me, we have to calculate the photoelectron spectrum. And it's quite complicated. It's relatively simple. So if you look here, we have it before and after. So we fold the calculated spectrum with the actual resolution of our system. So our resolution is compromised because the FEL has a bandwidth and the electron spectrometer has a finite resolution. So the electron spectrometer resolution for VMIs tends to be small, about 100. So at 25 EV, it's about a quarter of an EV. It's about 2% actually, it's not even 1%. But we get about a quarter of EV off the electron spectrometer and about another quarter, 0.3 of an EV off the FEL. When you fold the two of them together, you're talking about a resolution of full width at half max of about half an EV. So when we fold these with the resolution of our experiment, these are the photoelectron lines corresponding to neutral ionization. And these are the photoelectron lines corresponding to ion ionization. What's important about these is that there have been experiments done before on 2-photon double ionization, but we've managed to resolve them in at least, not perfectly. Okay, if you look at this component here, this guy here, this guy corresponds, it's a single ionization from krypton plus in a well-defined initial state and a not so well-defined final state. It's very difficult to do this. If you look here, we have two lines overlapped, but if you look at this guy here, it's a single initial state and a single final state. So what we've managed to do is, with a little bit of tweaking of the detectors and so on, is to resolve these spin orbit components for these guys. These guys were seen with synchrotrons, these guys here, and that hasn't been done before. And then that allowed the theorists to switch on some relativistic effects in their calculations. So the next thing you want to do is, because bear in mind, we have angular distributions, not just energies. So energies, you compare with theory, you can see lots of structure in there. I'll show you why that is in a second. But then you want to be able to calculate the angular distributions. So what do the angular distributions look like? Well, they depend on the kinetic energy of the electron, but they also have a dependency here on this parameter here, beta, which is known as an asymmetry parameter. And you can see here, if you have one photon ionization, so this is the photoelectron angular distribution, which is the same as angular resolved photoelectron spectroscopy. This is what you get from angular resolved photoelectron spectroscopy, the PAD. So for one photon ionization, you can see that the pattern that you should see depends very strongly on beta. And so in our case, you can see we were very close to small betas. If you have beta equals 2, depending on you know, are you ionizing from an s orbital or a p orbital? This is what these things tend to look like. For 2 photon, you end up with 2 asymmetry parameters. So in order to fit the distribution, you need to use this expression here, and it's got two parameters, a beta 2 and a beta 4. So there are two asymmetry parameters that you need to produce. So what we did is we took the angular distributions from these guys here, and then we fitted them. And so this is neutral krypton. So this is the experiment. And if you look at the full line here, that's the present theory. And there was a previous theory, which is also pretty good. And you can see it's up here, it's the dotted line. So as far as the neutral is concerned, switching on a very intense beam, we didn't see a huge difference in the angular distributions for these neutrals. And they compare pretty much with what we might have expected. What hasn't been measured, especially spin orbit resolved, because it couldn't be done, for example, with synchrotrons. If you go and look up the literature, calcium plus is one of the few ions where people have done electron spectroscopy. There's lots of ion spectroscopy with ions. So experiments done at the ALS in the States, done at Petra, for example, in Hamburg, done at Soleil synchrotron. It's easy. If you put a photon beam in to an ion beam, and then which is plus, and you generate 2 plus, it's easy just to measure the ions. The problem when you do electron spectroscopy is you dramatically reduce your signal because you're looking at electrons coming from a particular final state. And so electron spectroscopy of ions is really only now possible with, of ion beams, is really only possible with FELs. And in this case here, we're actually starting with a neutral, we're ionizing it with the front end of the pulse, and then we're ionizing it again with the back end of the pulse. And so you can see here that the theory is still a little bit wanting. There's no doubt about it. So the present theory is this blue line. So here's the three, these are the angular distributions for the 3 photoelectron lines that we see in going from krypton plus to krypton 2 plus. And you can see here that, you know, we have reasonably good, you know, we've got a decent looking experiment. We're pretty confident with the experiment, but there's really work to be done. Reference 29 is, again, you can see there's a significant difference between reference 29 and ourselves. That's a theory paper, obviously. So there's a significant difference there. So, and the problem is that they, in this case, they lie either side. We have a sort of a, you might look at this one here and think that's perfect. I caution that in this one here, we don't have 2 discrete features. What we have is essentially 2 lines, 2 photoelectron lines, which lie at the same energy. They're overlapping, and that's just completely accidental. But at least we've extracted these asymmetry parameters, and there's further work in the theory. To show you why it's complicated, it's not so bad in the neutral. So this is the photoionization cross-section. The yellow band here corresponds to the bandwidth of the FEL. And you can see there are some features, resonance features, but reasonably weak. And of those features, some of these are doubly excited states. They're not just singly excited resonances. But once you go to krypton plus, there are quite a lot of resonances, and you can see the scale here, 10 to 100 megabarn. There are quite a lot of resonances in the excitation channels in the ion. So it's quite a complicated business, and that's what's complicating these angular distributions calculations for the theorists. And so there's work to be done. So in summary on the krypton, and I'm conscious we're running out of time, we have 2 photon double ionization done, where we got fine structure in the initial final states. And so we've resolved that for the first time. The R matrix calculations, but done by our colleagues, are pretty good, great for the neutral, pretty good for the ion, and we're getting there. And the inclusion of these resonances, and if you go back, I published a paper quite a few years ago from the lab here, looking at not just krypton, but looking at the isoelectronic sequence, and these doubly excited states get even worse as you go towards more highly charged ions. And so there's still a lot of work to be done, but you know, we've done the first resolution, and we've managed also to resolve the spin orbit split components and challenge theory a little bit more, and hopefully that will stimulate a few more of the theorists like Stefan Fritschke and Pranela Deshmukh and loads of other people to work on that. I want to talk a little bit about photon to Auger electron emission delay time, and I'm conscious that, how long have I got? About 5 minutes, is it? Thereabouts?
You can
okay,
take 10 more minutes.
10
more minutes, no problem.
That okay? Yeah, great. So I want to talk about a process which is a ubiquitous process in atomic, molecular, and solid state physics, and it's Auger electron emission. And you probably know that if you start off with a very simple system, let's start off here with neon. So 1s, 2s, 2p, we'll make life nice and simple for ourselves. You can say here that imagine you have an X-ray, and what you might do is eject a K shell electron. So you eject a 1s electron, and now you're left with a hole here in the K shell. And then, for example, an L shell electron might recombine with that, which means there's some extra energy inside the atom. So you generate some internal energy. And that internal energy can be sufficient to ionize a second electron. So you start off with a primary photoelectron. You have a rearrangement or relaxation within the ion. So this is a singly charged ion. And then you end up with a doubly charged ion because you have a valence electron which is ejected. And so the question is, well, what's the time delay between here and here? And it will depend actually, of course, on the atom. And this becomes even more interesting when people look at them in molecules and so on. And so you could do a few things here. You know, there's time and frequency are conjugate variables. So let's go look at the width of this Auger line, and we can relate that back maybe to the whole lifetime. And people have done that. But the real question is, can you think in terms of time delays between here and here, or do you think in terms of phase shifts, or what way do you think about it? So this is Pierre Auger. It's kind of hard to get a picture of Pierre Auger where he doesn't look unhealthy, but that's a picture of Pierre Auger. This is Lise Meitner. You've probably heard of the Han Meitner Institute. This is Lise Meitner. It actually turns out there's quite a bit of a controversy at the moment about whether people should call it the Auger or the Auger-Meitner effect, because it turns out she published a paper in 22, which is effectively on the same idea of Auger electron emission, but she obviously didn't call it Auger electron emission, but she also didn't call it Meitner electron emission. And so there's quite a bit of controversy as to what you call it. For the moment, it's still been called Auger emission. I did see recently a talk given by somebody where they call it Auger-Meitner emission. But anyway, the point is we have a primary electron and a secondary electron, and we'd like to measure the time delay between them. So in order to do that, you need a big, long collaboration like the one I showed you. And so I can tell you that the first time we thought about doing this experiment, there was a Pearl, it's called Physics at EBITS and Advanced Research Light Sources, and it's run out of Wuhan University by Yaming Zhou and her colleagues, Roger Hutton and others. And they run this workshop every couple of years on ions and the interaction of ions with advanced light sources. And for 1 year, they were doing ICPEAK, so they asked us to run the Pearl conference, and a number of people came here. And we had a talk about how to measure these things at FELs and do it on a single shot basis. And I can tell you we've had 4, this is a recent paper, just out in January. It took us 10 years and 4 beam times and lots of variations on the theme here of people who joined and left and came back and so on. But, you know, guys like Adrian Cavalieri stuck with it, and I work a lot with Adrian, as did Gilles Dumi, worked quite a bit to try and make this kind of work, this guy here. And I spent quite a bit of time, but we started off the idea actually with a guy called Reinhard Kienberger with Adrian while we were here at a workshop. And the idea was to take something which was quite well known, which is atomic streaking. So bear with me and I'll try to explain this. So many years ago, Marcus Drescher, Uli Heinzmann, and Franz Krauss and a number of people, Adrian Cavalieri and Reini Kienberger in particular, they thought about this idea of how would you measure ultra short X-ray pulses. And so the idea was as follows. Imagine you had an optical laser with only a few cycles in it. And that optical laser, so imagine this is like a few femtoseconds long. So if you take titanium sapphire, the period here is about 2.5 femtoseconds. So you might have something like a 10 femtosecond pulse. And it might have an electric field which looks like that. And so imagine now you had a gas. And what you do is you focus this pulse here, which might be, say, 100 attoseconds long. generated by phase locking high harmonics. If I'm sure some people have worked on high harmonics or looked at high harmonics. And in high harmonic generation, if you play with the optical laser, do a thing called carrier envelope phase control and very short pulses, you can arrange matters and some filtering as well of the lower harmonics. You can arrange matters to generate, say, 100 attosecond X-ray pulse. That X-ray pulse, when it's focused into a gas, generates a replica of itself. It generates an electron bunch, which is a replica of the X-ray bunch or the XUV bunch. So imagine what you've done now. You've focused the X-ray into the gas and generated an electron bunch replica of the X-ray pulse. Now, depending on where that X-ray pulse is with respect to the phase of this beam here. So in other words, depending on where I generate it, if I generate it at this instant here, then I have a positive electric field and I shift the electron bunch energy to positive kinetic energy. If I generate the electron bunch down here, I generate it where the electron field has gone below zero, so it's negative, and I downshift the electron kinetic energy. So as I shift the time delay between the X-ray beam and the optical laser, assuming no jitter between them, then what I can do is I can shift the kinetic energy of the electron bunch up and down, up and down, up and down, as I change the time delay between the optical field and the X-ray field. And so what can I do? I can map out, in this particular case here, the electric field of an ultra-fast laser. Now that was done a long time ago. And the reason you could do it is you can use the same optical laser to generate the attosecond pulse as you used for doing this so-called streaking. So if you think about this, this looks like the oscilloscope trace or a streak camera trace of the optical pulse. What you've effectively done is generated a device, a streak camera, which allows you to map out the electric field of an optical laser there. What it really allows you to do is to measure with very high precision time. And so you have essentially a streak camera with resolution which is sub femtosecond. The key here is that this bunch here has to be shorter than half an optical cycle, because otherwise you just smear this out. So we thought a while ago, so we had various efforts to do this, and there's a big jitter between the optical pulses and X-ray pulses at FELs. And so what we thought was, why don't we make a different type of electric field, single cycle, so we know exactly what the field looks like, and one which has a cycle time which is, say, on the order of a picosecond or something. Because we knew that if you look at an FEL and an optical laser, the jitter here is going to be hundreds of femtoseconds. So this won't work. So what it meant was that if we could generate this field here, it's a terahertz field, essentially a single cycle terahertz field, then we wouldn't have to worry about the jitter, because if our pulse was up here, we could see it. If it was down here, we'd see it, because we'd simply measure the kinetic energy shift of the electron bunch. And so we could do things like literally show shot to shot where the X-ray pulse was with respect to the optical pulse, excuse me, in real time. And a couple of things happen here, by the way, because when you have, if you have this scenario here, right at the center, the electric field of your terahertz field is zero. But here, the field is negative, and here the field is positive. So what happens here? Here, this bunch will get downshifted in kinetic energy. This guy here will get upshifted in kinetic energy. So imagine you had a double X-ray pulse that looked like that, which produced a double peaked electron bunch, a replica, remember, of the X-ray. You have an electron bunch which exactly replicates in time and in profile the X-rays. But this guy here would be shifted to positive kinetic energy. The other thing here is that different parts of this bunch experience different fields. So they get broadened. So you have shifting and broadening. And by studying the kinetic energy shift and the kinetic energy broadening and calibrating the system, you can turn this into a timed streak camera. What we did for the most recent experiment was we knew that we'd be looking at time delays of a few femtoseconds as a time delay between the photoelectron bunch and the X-rays and the Auger. And so we needed to generate fairly short X-ray pulses on the order of a few femtoseconds, but we still have this jitter problem. So what we did was, so this is an OPA and did with some difference frequency generation to generate a 17 micron pulse. So with 17 microns, instead of having a period here of 2.5 femtoseconds, it'll be more like 70 femtoseconds. So we didn't need to generate a picosecond, but we generated a field which was about with a single cycle field with about 70 femtoseconds or so. And we did the same thing again. We basically hit the FEL pulse through a hole in a parabolic mirror. We focus in this case, a mid-infrared beam into the target. We do the same type of experiment, but there's a little trick that we do. So basically, if there's a phase shift, if you have a phase shift between the electron bunch and the field, you can calculate the change in kinetic energy. And it depends on the phase shift, it depends on the kinetic energy of the electron, and it depends on this thing, the ponderomotive potential. And you can calculate the so the ponderomotive potential is a sort of a field averaged energy for the electron in the infrared laser beam. So we have this mid-infrared laser, that's its frequency. That's the electric field, peak electric field value. And we can calculate UP using this expression. We can substitute UP in there. We know what the kinetic energy is because we use neon actually in this case. So we know what the ionization potential is and all the rest. So we can work out the kinetic energy. And therefore, we can relate the kinetic energy shift to the phase shift between the electron bunch and our mid-infrared laser field. Now, in fact, the problem is that you've got this jitter which is going on between our mid-infrared field and our X-ray laser. And so if you consider this to be the mid-infrared field, here's the photoelectron replica. Here's the Auger electron replica. Excuse me, they have some time delay between them on the order of femtoseconds. Then as these guys are jittering around, what's going to happen is you're going to get a shift in kinetic energy and a broadening, which varies between these two guys here. But it all depends on where this field is with respect to that. So what we do is we run the experiment with thousands of shots, and we measure the two kinetic energy differences. So we isolate the photoelectron peak, known as photoemission here, from the Auger peak, because they're separated in kinetic energy anyway. And then, because they're separated in energy, we then measure, each of them are shifted, and they're shifted differently because they are born or appear at different phases of the mid-infrared field. And if we plot the Auger peak energy versus the photoemission peak energy, we should get an ellipse which looks like this. So this is a bit like Lissajous figures, you know, where we plot two things which are phase shift with respect to each other. So you think in terms of, well, I'm driving my electron this direction and this direction. It's not true. It's a sort of a fiddle, right? But think in terms of Lissajous figures and think in terms of ellipses. And so you can think in terms of this thing as a sort of a classic ellipse where this phase advance is going to depend on y1 over y2, where y1 is the ellipse y-intercept and y2 is the maximum value of y. So in other words, excuse me, this is what we actually measure. So in practice, we measure the shifts. So bear in mind, this jitter's going on, we're getting lots of shots. We measure the shift between the photoelectron and the Auger electron. We plot those and we get an ellipse, and you can pick out different points on the ellipse corresponding to different situations where you know that the delay between the Auger electron and the photoelectron are fixed. It's just they appear at different phases of the field. And you can see here you essentially have 180-degree phase shift. So you can see that this field is flipped over. So positive, negative, positive becomes positive, negative. And so you can pick out different regions on the ellipse here. And that actually allows you to measure the time delay. And so we measure the time delay between the photoelectron emission and the Auger electron emission. And we could measure it with, you know, an uncertainty of a couple of hundred attoseconds to be about 2.2 femtoseconds. So we call this self-referenced streaking. It can work with all SAS FELs around the world. It can reach a resolution of less than a femtosecond. In the future, if we have better stabilized infrared laser systems, CEP stabilized, we should be able to get ourselves down below 100 attoseconds. A lot of it depends really on the quality of our ellipse here, which depends as well on the width of the FEL and so on. One of the really important things about X-rays, and one of the selling points they're using on X-rays, which we've all known for 100 years now, but of course they're still selling it at FELs, is site specificity. Because if I can tune if I have a molecule with lots of different atoms with different atomic numbers in it, then as I tune the X-ray wavelength, I can select out different atoms in the X-ray, which sit at different sites. So I have site specificity. So you can also imagine that we can measure some of these Auger whole lifetimes and see if the molecular environment has any impact. We know already that we can see chemical shifts, of course. But the question is, are there shifts in the lifetimes of excited states or which have very short lifetimes, in other words, whole states that are affected, and can we measure those directly? And we can do all kinds of nice fancy things, because you can combine infrared lasers with X-ray probes and study things like wave packets. When they come to a conical intersection on a molecular energy surface, they can split. And so one of the interesting things is to look to see at what points in time does that splitting occurs, and what sort of effects you might see afterwards. Very last thing just to say to you, we are now moving into molecules. I never thought I'd move into molecules, but I'm moving into molecules. And just to say to you, we've recently done an experiment at the Fermi FEL, which is just an outstanding machine, absolutely outstanding machine. This is a fully phase coherent free electron laser, which will give you photons from 10 eV to a couple of 100 eV, and you have full control over the beam. And so we did an experiment, and I won't bore you with the details, but basically we did what's called impulsive alignment. We use a femtosecond optical laser with a strong electric field to align a molecule, dipole align a molecule, take it away, and then let the molecule rotate. And because we made it very cold, we could actually see. So this essentially is the ion emission as a function of time after we hit it with the X-ray FEL. And you can see the molecule is rotating. It has a rotational temperature actually of only a few Kelvin. The most important thing, and I haven't time to go into detail, is that we actually studied revivals in the electron spectra for particular molecular orbitals. And we're studying those at the moment, because we are looking to see if we could drive a single VUV photoisomerization process. I'll finish with this just to say there are lots and lots of people involved, but I do have to mention Lazarov Stefan and Gregor Hartmann when it comes to here, because they're the people who mainly worked on that. Dan Haynes, Adrian Cavalieri, and Reini Keinberger, I have to mention there. And on the very last thing, which we're currently working on, it's a bunch of people at the Fermi FEL and Koyoshi Ueda. I want to congratulate you on your first 25 years and hope that your next 25 years is equally successful, if not more successful, and that your research and your teaching, your graduates continue to be world leaders. And I wish you well on that. And I'm going to finish at that point. Thank you very much.
Thank you, John, for that very illuminating talk. I'm just waiting for the questions in the Q&A chat box. Meanwhile, I have just a few questions from my part. Mm-hmm. These femtosecond lasers or the attosecond lasers can also generate these plasmas. So can we have these kind of photoelectrons generated in the plasmas?
Yeah, you can do this with attosecond beams. The problem is that there's so little, too few photons in those pulses that you can't do single shot spectroscopy. So if I was to say what the kind of USPs, the unique selling points of FELs are, they're very, very expensive. So you're not going to have them in your lab, but they allow you to do single shot spectroscopy, because you're talking about 10 to the 12 or 10 to the 13 photons in a single pulse, say a few tens of femtoseconds long. With the high harmonics, again, you're talking about tens of femtoseconds, but maybe 10 to the 5 photons at 100 EV, 120 EV. With the attosecond pulses, maybe 10 to the 4 in 100 attosecond pulse. But when you start to look at those attosecond pulses, and particularly some of the projects around the world right now, you know, Ferenc Krauss and people are now generating, 200 EV pulses with, 10 to the 7 photons in 100 attoseconds. So when I take the total energy and I divide it by the time, and then I focus it to a very small spot, suddenly I get up to high intensity. I can get to 10 to the 14 10 to the 15 watts per centimeter squared at 100 EV off a nanosecond laboratory-based source. So you can start to compete in some of the high field experiments. The problem with 100 EV photon is that it's very hard to drive nonlinear processes. So for example, at 10 to the 15, I can generate field ionization with an optical laser. I predominantly have a 1 photon process at 100 EV at 10 to the 15, because at such high photon energy, photon processes basically win, you know. So
I have another question in the chat box.
Yeah.
How, I will just read the question for you.
Yeah.
How electron kinetic energy is obtained from a radial distribution?
Yeah, so we don't need the radial distribution. So basically, if I show the, let me just put this up for a second and go back to the picture. Sorry, which, you know, I'll just share my screen and let me go back to the picture. So, oops, back here somewhere. Yeah, this guy here. So this is the radial distribution here. And so if you look at R, this distance out here, this is kinetic energy. And the reason is when the electrons go in to this Einstein lens system, that the higher the kinetic energy, the more they're deflected. And so high kinetic energy electrons are deflected up here and down here and down here and down here. So these are the high kinetic energies. And the low kinetic energies obviously have less deflection. So the degree of deflection depends on the kinetic energy. And we can calibrate this because we can put in gases where we know the photoelectron energies, we know the ionization potentials. So we can calculate the corresponding photoelectron energies, and we can calibrate that space there. So this is an image taken out with this is actually done with a CCD in the end. It's a microchannel plate, a phosphor, and a CCD. And so the kinetic energy just depends on the radial position. So the way to look at this is kinetic energy is R, and angular distribution is theta. So you can pick any R theta, and you have an angle of emission at a particular kinetic energy. That's the way to look at that.
Thank you, John, for that. I have another question in the chat box. This is by Professor Riju Isaac. The question is, how good is the synchronization in the SAS FELs?
Yeah, it depends. It's pretty poor. So, and it's getting better. So if I go back to when I started first in 2005, and we did an experiment at Daisy, we had 500 femtosecond. So we measured the jitter. We just measured the time distribution of the jitter. And we had 500 femtosecond full width at half max. So half a picosecond jitter. So of course, if I'm doing molecular physics and I'm looking at rotational spectroscopy, that's fine. But it's not very good for electron spectroscopy. Very recently, two things have happened. One is that in some free electron lasers, they stripped out all the copper cables and they put in fiber optic networks for the RF, for distributing all the various synchronization signals around the system. And at Daisy, they managed to reduce that RMS, not RMS, but full width at half max jitter from 500 femtoseconds down to about 100. It's actually 90. The other thing which has happened, and it's even better when you go to places like Fermi, is that the laser which creates the electron bunch which goes into the linear accelerator is the same laser that they amplify and use at the end station in order to do optical laser synchronization with the FEL. So in other words, they use the same laser, they split the beam, and now they get down to a few femtosecond jitter. But there it's very fancy, you know, they're using that laser to do their injection seeding, they're using that laser for their synchronization. In the other big X-ray FELs, it's a separate laser system, and that's why the jitter is bigger. But think in terms of 100 femtoseconds. If you think about proposing an experiment at XFEL or LCLS or somewhere, think in terms of, I'm going to have 100 femtosecond jitter at my SASI FEL.
There is another question which has come to the chat box. Is why krypton and neon were selected? Any particular importance for them?
Yeah, so Sorry, what was the question about their importance? Sorry, I missed that.
Yeah, any
Oh,
particular
any particular
importance
importance.
for selection?
Yeah, they're not molecules. So they're not hard. So whenever we're trying to demonstrate a principle, we always try to go for the simplest system possible. And so we tend to avoid molecules unless we have to. And so we wanted in the first case to demonstrate 2-photon double ionization near its threshold. And so the simplest thing you can do that is in an atom. And of course, at DAISY, it was easy enough to produce 25 EV photons. So we wanted to do it in an ion, and we wanted to do it so that the electrons would have a kinetic energy which is very low, because we wanted to study 2-photon double ionization with low kinetic energy. So it turned out that 25 EV was easy at DAISY. Krypton plus is about 24 EV, so we could generate 1 EV electrons. And that's the only reason why. And that was purely driven by, it's just driven by curiosity. There's obviously no application there. In the second case with neon, we chose neon because it's very easy to get at LCLS and use, and there's no health and safety considerations. And also we could separate out the Auger and the photoelectron in kinetic energy. So when we looked on our electron detector, we could separately see a peak due to the photoelectron and the Auger electron, and they were well separated in energy. And that was important to us because we needed to study the broadening and the shifting of those as they varied, as those electrons were born into different phases of the terahertz field. And so we chose neon for that reason. But importantly, this can be done in any molecule, because the great thing about X-rays is, I can essentially choose my K-shell for any atom, and they're all different. And so I have great selectivity with X-rays. So there's no reason why that second technique, self-reference to streaking, cannot be applied to surfaces, to molecules, as well as to atoms. But we chose neon just because, if we chose UF6 or something, we'd have health and safety people not allowing us to do it. It's America.
Thank you, John. That was a very exciting talk and very good session that we had. I think we'll wind up because we don't have further more questions in the Q&A session.
Pleasure.
I hand over to Dr. Praveen.
Thank you, Professor Costello, for a wonderful talk and for being part of our Silver Jubilee celebrations. And it would have been better if you were here with us for giving the talk. And we hope that we will manage to bring you over in the coming years sometime. So thank you very much. Thank you once again. Sure. Thank you very much.
I'll be back in India. Don't worry. When I am, I'll come visit.
Sure.
I'll come
Most welcome at any time. Sure.
Thank you very much.
Thank you very much.
It's a real pleasure and an honor. And I wish you well for the next 25 years. Pramod, great to see you.
Thank you, John.
Praveen, it's great to see you. And I wish everybody well there. All the best and take care. Bye-bye.
Thank you, John. Bye.
Bye-bye.
Thank you, everybody. Thank you, everybody, for joining us for this seminar today. Thanks.